So now that you've heard a bit about the background of modern Java, how it's got multiple paradigms, let's pretend for a moment like the object-oriented stuff is well handled and under our belt, and let's zoom in on the functional programming features, starting with so-called Java Lambda expressions, which are very cool. So I'm going to show you a bunch of examples now to illustrate how these features work, and this will give you some hints on the assignments, and you'll use this material throughout the rest of the course. The assignment 1 you're going to be doing will give you some features. Assignment 1B will give you some features to work with, but we'll also go on well beyond that when we do the other parts of the course. So it's important to have a good foundation in the Lambda expressions and method references and functional interfaces we're about to cover. So what is a Lambda expression? A Lambda expression is essentially an unnamed block of code with optional parameters that can be stored, passed around, and then executed later. And that executed later part could be executed in another method, it could be executed in another thread, and so on and so forth. So here's a good example. We're going to make ourselves a new thread using the Java thread object. And if you know much about a Java thread, what it's going to do is it's going to create a new activation stack with activation records in order to run methods in a different thread context. And there's a constructor for the thread class that expects to take an instance of something called a runnable. And we'll talk more about a runnable shortly, but a runnable is a very simple functional interface that has a single method called run that takes no parameters and returns no result. So it's just a way to start something running in a new thread. And here's a way to pass a runnable to the thread constructor using a Lambda expression. And first, we just have to look at a little bit of syntax. So this particular Lambda expression, as you can see, has an open-close paren as its first piece of syntactic sugar. And that simply says that this Lambda expression takes no parameters. It doesn't take any arguments at all. And that's exactly what the run method in runnable does. It doesn't take anything. So we just say open-close. This is simply here for syntactic sugar. Then there's a little arrow, and the arrow separates the parameter list, or the lack of parameter list in the case of runnable, from the body of the Lambda, the actual implementation itself. Here is the implementation of the notional run method in the runnable. And as you can see, it's just a simple statement. It says system.out println hello world. So it's basically the kind of the canonical starting point for all programs is to print hello world. And our example here is no different. So we're printing hello world using a Lambda body. And as you can see, that's defining the computation that we're doing in this case. And of course, what's going to happen here when we start the thread is it's going to go ahead and run in the background. We'll get to that in a second. So this ability to pass Lambda expressions in places that used to expect references to objects leads to a really nice capability in Java called behavior parameterization. Now, you're already familiar, I'm sure, with parameterization of data or values. So historically, you pass a method, an integer or a double or an employee record or a string or whatever. That's classic data parameterization or object parameterization. But with Lambda expressions, and as we'll see shortly with something called method references, we now get the ability to do behavior parameterization. And as you can see from this little diagram here, which is explained further in the link at the bottom of the page, the Lambda expressions are very flexible and also relatively concise. And we'll compare and contrast that in just a second with some other variants like anonymous classes, which are not as concise. So what happens when we say new thread, Lambda expression system.out.println hello world .start, that goes ahead and creates a new thread of control, which is implemented by this stack of activation records, and that will then go off and run concurrently to the calling thread that started it. And that'll run in the background and do its thing. Again, I'm not going to go into a lot of detail at the moment about threads, but just take it on faith that it runs something in the background, and in this case, it's going to print out hello world on the console. If you want to learn more about threading, take a look at the link at the bottom of the page, or go look at my playlist for concurrent object-oriented programming that goes into this in great, great detail. You don't have to pass a Lambda expression to the constructor literally. You can also go ahead and create a local variable. In this case, I make a variable called R of type runnable, and then I go ahead and assign it the Lambda expression. And that Lambda expression is actually not evaluated when I do the assignment to runnable R. Instead, it kind of packages it up, and then it can be used to be passed as a parameter to the thread constructor. So when we say new thread R start, that passes in that runnable Lambda expression, and then that Lambda expression will be called in the context of the thread. So kind of going back to the original definition, it's an unnamed block of code that can be stored. Here we're storing it in a parameter called R. We're passing it around as a parameter to thread, and then we're executing it later in the context of the new thread once the thread has been started. So that's just showing that you can pass these things around as parameters. Why do we like Lambda expressions? We like them because they're very compact, and they only focus on the computation or computations that we're trying to perform. So think of it like a smart car, right? It's very small, very lean, and saves you lots of things. Well, what would be an alternative way of doing things? An alternative way of doing things would be to use something called an anonymous inner class. And this example that I've highlighted down at the bottom of the slide illustrates the classic way of doing this. This goes right back to the beginning of Java, where you can make these so-called anonymous inner class objects. And what you see here is we make ourselves a new runnable that's anonymous. So we say new runnable, open curly brace, public void run, open curly brace, system.out.println, hello world, close curly brace, close paren, dot start. So you can see here that that's a heck of a lot more code than this. This is just focusing on the computation. This is requiring you to add lots more syntax. And so what we end up with when all is said and done is just more code to write, more code to read, more stuff, sort of syntactic vinegar, if you will, sort of the opposite of syntactic sugar. And it's not the end of the world, but it gets tedious and error prone to write this and read this. And you end up having a higher chance of getting carpal tunnel syndrome because you're typing more code. There's some other things to be aware of with Lambda expressions. You can use them to access variables from the enclosing scope. And these can either be so-called final variables, where you say this is sort of a constant that never changes, or in modern Java, starting with Java 8, there's also something called an effectively final variable. So here's an example of an effectively final variable where we're having a local variable called answer that we give the value 42 as the value. So the answer, 42 is the answer to life, the universe, and everything. And then we're going to go ahead and pass that answer variable into the Lambda expression. And so when we print something in the background in the other thread, we're going to say the answer is 42. So answer is passed in as what's called an effectively final variable. An effectively final variable is a non-final variable that doesn't change from the point where it's assigned or initialized in this case to the point where it's used. So you can read more about effectively final variables in the link at the bottom. Those were added with Java 8 in order to be able to do things like this. So you don't actually have to make something a final variable, but you can use it in a context that's a different scope, in this case, a Lambda expression scope. Lambda expressions are most effective when they're stateless and they have no shared mutable data. Again, remember, shared mutable data is the root of all evil in concurrent programs because it leads to race conditions where the state of the variable is corrupted when multiple threads simultaneously try to read and write to it or load and store it. So as you can see here, this particular example is indeed stateless because we're not changing anything, we're just reading something, and so that will not have any problems with race conditions in concurrent code. So that's a good thing. This is also very important when we start using our parallel streams framework, which will come probably in a few weeks. We'll probably get to this maybe by the middle to end of September. And stateless Lambda expressions are extremely valuable in parallel streams because each of the Lambda expressions has no side effects, so we can run them in parallel in different threads in a thread pool that's used to perform the computations in a stream. If that doesn't make a whole lot of sense yet, don't worry about it. We will get there and cover that in great detail as we get a little further on in the course. Okay, so now that I've kind of given you an overview of Lambda expressions, let's kind of summarize some of the benefits. What do they buy you? So one thing you can do with Lambda expressions, which I kind of hinted at before, but we'll learn more about now, is you can work with multiple parameters in a much more compact and concise manner than by trying to use anonymous inner classes, which are usually our kind of straw person whipping post to demonstrate why you should not use the old school way of doing Java, but instead use the new version. So this particular example is available in my GitHub repository in the Java 8 EX1 folder. So what we have here is we've got an array of names that are represented as strings. So we have name array, which is an array of the names of these people. And then I'm going to show you a couple of different ways to sort this array. So the first way we're going to do it is by using the classic anonymous inner class syntax, which, as you can see here, is very tedious, very error prone, very verbose. So I think about it kind of like a gas guzzling Humvee. It's way overloaded for what you might need it to do. If you just want to drive to school and park, you probably don't need a Humvee. So in this case, I'm not even going to try to explain it to you. It's just a lot of syntax that's doing the anonymous inner class. Let's contrast that with how to do this with a Lambda expression. So I said before, the Lambda expression is kind of like a smart car. It's much more concise, much more lean. I don't think it's mean, but it's lean. And you can see here that we say arrays.sort name array, just like we had done before. That part's the same. But then what comes next is much more concise. So we say open paren s comma t, close paren, which is just shorthand for string s comma string t, which leverages modern Java's type inference capabilities. It can deduce the types just from the names. And then we basically say compare s to t while ignoring case. So uppercase and lowercase characters will be compared the same. And I think you'll agree with me, this is a lot more concise than the earlier approach that we see up here, where you have a lot more to do. Reading this code, it's like, what the heck is going on? Reading this code, once you know how to read Lambda expression syntax, it's like, oh yeah, we're comparing S and T, ignoring case. So what's happening here is we're omitting the name of the method, we're omitting all the extraneous syntax, and we're just really getting down to the heart of the computation. So it's a good practice to use Lambda expressions when you're programming with modern Java whenever you can. And in fact, it's such a common thing to do that modern IDEs like Android Studio or like IntelliJ or Eclipse and so on actually automate converting between anonymous inner class syntax to Lambda expression syntax whenever it can be deduced by the IDE to make that transformation in an automated way. So if you hover your mouse or your pointing device or your finger or whatever you're using as your pointing device over top of anonymous inner class code, you'll typically get a little pop-up and it'll give you an option for doing the automatic conversion of the anonymous inner class into a Lambda expression. So not a bad thing to get used to doing. The last thing I'm going to cover in this kind of introduction to Lambda expressions lesson is to describe how you can implement a variant of something called closures with Java Lambda expressions. So you can implement kind of a simplified variant of closures. And this, again, this example appears in the EX1 folder in my GitHub repository. So the example is called closure example. And first that, of course, raises the question, what the heck is a closure? Well, if you look at the Wikipedia entry for closure, you'll see a closure is an object that stores a method together with an environment that has at least one bound variable. So what does that mean? A bound variable is just a fancy name for, a bound variable is something that has a name that's associated with a value, such as a number or a string. So you can see in this particular example, we have the private field mres and the method parameters, s and n. Those are bound variables, and they get bound to whatever they're assigned to. So you can see here what we have is we've got a factory method called make thread closure that's going to take a couple of parameters, and then it's going to go ahead and make a new thread. And in that thread, we're going to access and or update some of the bound variables. So as you can see here in this background thread, we're going to print the value of string s, and we're going to print the value of mres after being updated with the value of n. So s and n are parameters, and it turns out we can only read their values. I think I'll mention this more in a second. But mres is a private field, and so it can actually be updated. So it's both read and write ready. So this is going to go ahead and print those values out. It turns out that this is one of the things that makes Java Lambda expressions kind of a variant of closures. There's some limitations with what you can do with the bound variables. You can't update parameters. You can only update private fields. So what happens here is we have a constructor called closure example, which calls make thread closure. It passes in the string result equal, and it passes in the value 10. So those are the values that get bound to parameter s and parameter n in make thread closure. And what we get back from make thread closure factory method is simply a thread. And when we call start on that thread, it'll go out and create a new thread, print the value of result equal, and then it'll say mres plus equal n. And so it'll go ahead and print out result equal 10. And if we call it again, it'll keep incrementing mres. And then we call join just to wait for the thread to complete. Not necessarily the most profound example of concurrent programming, but enough to illustrate the idea that we've created a thread object that gets bound with these parameters that are passed to it. And that allows us to implement a variant of something called closures. So that's the end of the overview of Java Lambda expressions. We will see that Lambda expressions figure quite a bit in other parts of the class, so it's important that you have a good feeling for how they work. And you'll get a chance to learn how to implement Lambda expression related code when we do assignment 1B, which will be coming out after you finish assignment 1A.